let's talk a minute about vorticity on this finite wing. So here's our finite wing, and from airfoil theory, we know that in order to create lift, there must be some vorticity that is in the spanwise direction. Okay, so our vortex filaments would be in the spanwise direction. However, from the physics of from the flow over a wing, we know that we're going to have some vorticity trailing the wing as well. Okay, creating that vortex sheet along the trailing edge. And so we're going to find that we need to actually place these or look at this vorticity as a distribution that would run from the vortex sheet, and then would actually turn and move along the wing and then be shed on the other side. And so we can draw this vorticity. This is how the vorticity is distributed along that wing. And there's now a vortex filament can't change strength along its length. So let's say that any one of these could have a strength of gamma, or we could have gamma of z, for example, if we use z as the spanwise direction there. But little gamma would be a distribution, and capital gamma would be the strength of a single vortex. But that gamma, that the strength of that vortex can't change along its length, but it can change direction. And so in order to capture both the trailing vorticity and the spanwise vorticity, it would need to take a shape that looks something like this. Another thing that we learn here is if we were to cut this wing and look at a slice here at one of these airfoils, we'd see that the spanwise vorticity has a certain strength, and as we move to a neighboring slice, the change in vorticity, or the change in lift, is related to how much vorticity is leaving or exiting that trailing edge. So the change in lift along the wing is related to the strength of the vorticity in that sheet. Now, in 2 dimensions, we're familiar with the Krajkowski Law. The Krajkowski Law, which says that the lift per unit span, I've got it tilde up there because that's a 2-dimensional lift per unit span is equal to rho v infinity times gamma, or the strength of the vorticity of the object that we're looking at. Now, we can, on an airfoil, we like to actually look at little gamma as a function of s, for example, if s is the distance along the surface there. And so capital gamma was actually the integral of that gamma of s ds. Okay, so we actually integrated the vorticity around that airfoil, or the vorticity distribution, and we could come up with a capital gamma, and capital gamma is the total vorticity acting on that airfoil, and it's directly proportional to the lift by the density and the velocity. Okay, so we're familiar with the Krajkowski Law. Well, there's a 3-dimensional analog to that, and that is called the Vortex Lifting Law. Okay, so the Vortex Lifting Law says that a differential force vector is equal to rho times the vortex strength times the velocity vector cross dl. So let's look at some vortex here that has a direction, and we'll just draw it in this direction here. So that's a right-handed rule, and it's got a strength of gamma. And we can look at just a differential length of this vector. We'll call that dl, or of the vortex. And dl has a direction. It's actually a vector of differential length here. And then we've got some free stream velocity here, v infinity, or we'll just call it v for now. And that so that's our velocity that is meeting up with this vortex here. And if we multiply that by the density rho times gamma, which is the strength of that vortex, it will produce a differential force, dF, in the direction that is perpendicular to both v and dl. Okay, so this is called the Vortex Lifting Law, and it's basically the 3D analog to the Krajkowski Law that we're familiar with. So there are two things that we learned from this. One is that the differential force dF is perpendicular to dl and v. Okay, so the force is always perpendicular to that differential length along the vortex and the incoming velocity. And so that's the first thing we learn. And number two, if there is no force being generated by that vortex, then v must be aligned. So actually, let me back up here. If dF equals 0, and of course if gamma is non-zero, then v must be aligned with dl. Okay, so this has two important implications. So let's look at the first one here, that the differential force is always perpendicular to dl and v. What we're going to find is that the only vorticity here that contributes to lift is any vorticity that's aligned with the span-wise direction, or that is perpendicular to the incoming velocity. So any vorticity that's aligned that's in this direction, or the chordwise direction, does not contribute to lift. That's what we learned from number one. And also, I guess from number one, we learned, because this vorticity is, we call this bound vorticity. It's bound to the surface. Okay, and it's that bound vorticity that is bound to the surface that produces a force. Now, I said that it's only the vorticity that's in the spanwise direction. I guess more correctly, what I should have said is, any of this vorticity that's not aligned perfectly with spanwise direction will still create a force, but it's dl cross v. So we get the most lift from the vorticity that is aligned perpendicular to v. Okay, and these other, as we have vorticity that's being shed, and it aligns itself with the trailing edge, it reduces its generation of lift, because the cross product, because it's aligning itself with the free stream, and so the cross product decreases. The magnitude of that cross product decreases. Okay, so secondly, if dF equals 0, or the force is equal to 0, then v must be aligned with dl. So that's the case out here. We don't get any lift out in the shed vorticity in this sheet out here, this shed vorticity sheet. But and so what we learned from that is that this vorticity must be aligned with the free stream. Okay, and because of that, and it actually aligns itself with the local free stream. Or free stream. And so what happens is this vortex sheet will begin to roll up, as I explained earlier. It will roll out into these main two vortices that get shed from that wing. Okay, so that vortex sheet will eventually roll up into two very strong vortices that are centered just inboard of the wingtip there, and it's kind of the center of vorticity. It all gets sucked into those two main vortices. Okay, so we're going to use our understanding of vorticity here and this vortex lifting law to study the aerodynamics of finite wings, and we're going to start by looking at Prandtl's classical lifting line theory.